Okay, my friends, so let's smash together this last final step, visualizing the decision tree regression result in high resolution. Alright, so we're gonna do kind of the same exercise as what we did previously with the SVR. You know, that funny exercise where we start from the polynomial regression code for the visualization of the results, meaning this one. So we're gonna start from this code, and then the exercise for you will be to make the right change or changes in order to make this work for the decision tree regression model. If we did this successfully for the SVR model, well, it will be a piece of cake to do it for the decision tree regression model, because indeed no feature scaling was needed, and therefore we won't have to play with the transform method or the inverse transform method, and therefore you will just smash this. Okay, so let's do this. That's the exercise. So let's take this whole code here, which plots indeed the regression curve in high resolution, but for the polynomial regression model, let's paste that right here in the new code cell. And now, well, there you go. Please press pause on the video and make the right change or right changes in order to make it work for our decision tree regression model. Okay, good. So now I'm going to implement the solution with you. And let's start with the obvious change. Let's replace polynomial here by, well, decision tree. Okay, and then what was the change or changes you had to make? Well, as I told you here, it's super easy. You just have to change two things in actually only one row, which is row number 4, right? Because this row number 3 is totally fine, because here x and y are on the right scale, because no feature scaling was applied, so that's fine. And here, well, the obvious change that we have to make is, of course, to first replace this regressor by the right name of the regressor, which is regressor. All right, good, regressor. And then here, remember this polyreg transformation object was used to transform the matrix of single feature into this matrix of the same feature at different powers, power 2, 3, and 4. And this time here, we absolutely don't need that because we're not doing polynomial regression, so I'm removing this, and then also a parenthesis here. And now, guess what? Well, that's done, right? That's the simple visualization code when you don't have to apply feature scaling and you don't have to transform your matrix of features into powered features as in polynomial regression. So that was as simple as that, I told you, right? But now, that was the good news, and now I have some bad news. You're going to see that the results are not going to be pretty, because indeed, let's do this now. Let's execute this cell. There you go, playing, and here are the decision tree regression results. I really want to say this again. The decision tree regression model is really not the best adapted to two-dimensional datasets, with only one feature and one dependent variable. But once again, I'd like to remind that the implementation we have here can be very easily adapted to any other datasets, and I will show you what to do at the end of this tutorial, what to change in this code. But I still wanted to show you the decision tree regression results in 2D, and so why isn't this pretty? Because what this decision tree regression model simply did was to take the real results, the real salary for each position level, and then for all the position levels from position level minus 0.5 and the position level plus 0.5, well, it predicted the salary to be the same as the position level in the middle. All right, so that's what it simply did, and that's, understandable and intuitive, to understand, because you know how decision trees work. They work by splitting the data through successive nodes, and so at the end, you get different ranges of the features where the prediction is the same. And so here, all the predicted salaries in this range of position levels are just the same, and that's why we have this stair-looking like curve up to the last position level. And of course, here this is not continuous. This is actually a vertical bar. So the regression curve here is not continuous. We jump from position level to the next one every step of one. Okay, so not pretty at all, not relevant at all in 2D, but I still recommend to try the decision tree regression model for higher dimensional data sets, because indeed it can actually have great performance. Okay, so good to have said that. And now just a quick bonus. I'm going to show you that in low resolution, this makes absolutely no sense, because you will see what happened. I'm just going to add a code cell here. I'm going to take everything from here to here only, and then I will paste that here. Then I will just replace xgrid here by x and xgrid here by x also. I'm going to plot this, and this is the curve in low resolution. And as you see, this absolutely not makes any sense, because now since we only made the predictions for the integers, going from 1 to 10, well, of course, since you understood that the predicted salary of the position level number 6 was just the real salary itself, right? Because it was trained on the whole data set. So here this absolutely doesn't make sense, and therefore that's why I clearly not wanted to include that in the implementation. All right, you understand now? So now I'm going to finish this tutorial and this section also by showing you what you would only need to replace when applying this decision tree regression model on your future datasets in higher dimension. So let me show you. Let's take the cells one by one. Of course, you will still need to import the libraries at the beginning. Then when importing the dataset, you will of course need to just replace the name of the dataset here, and then maybe to include the first feature, it will probably be a numerical feature, with numerical values. So make sure to not forget to maybe replace this 1 by either 0 or deleting the lower bound here so that you include all the columns except the last one. All right, so going back to 1. All right, and then here, of course, you keep this, but make sure that indeed the dependent variable is at the very last column of your dataset. Okay, and then you need to check in your dataset if there are any missing values. And once again, if you have a huge dataset, well, I would just recommend to apply the missing values tool of your data preprocessing toolkit to your whole dataset so that you don't have to check where they are. And even if there are not any missing data, well, the inputter will just leave your dataset the same. Then I recommend to check if there is any categorical data, in which case you would have to apply your either one hot encoder tool if there is no order relationship in your categorical variable, or the label encoder tool if there is indeed an order relationship, like for example the size of a cloth, or well, actually the position levels of a company if they are collected in strings. So don't forget to check that out. And then once again, you don't have to apply feature scaling, because indeed the decision tree regression model works with splits. It splits your features in different successive ranges, which is thus a technique that absolutely doesn't need feature scaling, right? It doesn't have to do with any coefficients or whatsoever. It is just because you split your dataset through different nodes in order to collect in different final ranges your final predictions for different ranges of values of the features. So you clearly don't need to apply feature scaling. All right, and then let's see what we have to do next in order to, adapt it to any dataset. So actually that's the good news. Here you don't have anything to change unless you splitted your dataset into a training set and a test set, in which case you would have to replace x and y here by x train and y train. Then feel free to predict any new result you want. And if you have several features here, well, instead of putting the single value here, you would have to put the values of other features like 6.5, and then if you have, let's say, the age, you can put 30, and then if you have, I don't know, for example, the number of years of experience, you can put 5. That's how you would predict a single observation when you have several features. Okay, good. And then final important thing to understand, if you have a dataset with multiple features, well, this is absolutely not relevant, because indeed this is only used to visualize the regression result in 2 dimensions, and therefore if you have several features, you will have a dimension higher than 2. So you won't be able to plot anything here. Okay? So you would just have to delete that cell and delete this text cell as well. And that's only what you would have to do in order to make this decision tree regression work for your future multi-featured dataset. All right, great. So congratulations. Now you added this new machine learning model in your toolkit, and especially in your regression toolkit. So congratulations. And now we will tackle together the final regression model of this part 2, which will be the random forest regression, and which we will smash in no time, because you will see that it will be almost the same as the decision tree regression model. So either you'll join me in the R tutorials if you want to learn R, or you'll join me in the next section for the next practical activity on random forest. And until then, enjoy machine learning.